All right, so this particular video is going to be on alkanes, just an introduction to the different types of alkanes, like acyclic alkanes, cycloalkanes, and then just a couple little vocabulary words, if you will. But first, let's kind of define what alkanes are, and then we can classify them first and foremost as acyclic as well as cyclic. Okay, and so the general chemical formula for acyclic alkanes is C sub N H sub 2N plus 2. And then for a cyclic, it is C sub N and then H sub 2N. And this is where N is equal to the number of carbon atoms, okay? So for example, if I had 6 carbon atoms, which are very easy to count in the skeletal structure, we would do, this is like parentheses, and so 6 times 2 is 12 plus 2 is 14. So that means for an acyclic alkane, if it has 6 carbons and nothing else, then that means we have 14 hydrogens, okay? And when a particular substance or an alkane has as many hydrogens as it can possibly have, in this case 14, it is said to be saturated. Okay? And this has max number of hydrogens. Okay, I'm going to put a little line here just to kind of help differentiate between the two. Okay. And then another thing about acyclic alkanes is that they are typically going to be either straight chain or something called branched. Okay, and now we'll kind of identify what that is. So for straight chain, it means exactly what you think it would be. So if we have, let's say 1, 2, 3, 4 carbons, right? That's just a straight chain of carbons, whereas branched would be if we had something coming off of it. So there's like a branch coming off of that straight chain, okay? And so this would be branched, and this could be straight chain, okay? Now, these are obviously very simple examples of straight chain and branched. We could have extremely long straight chain as well as very intricately branched acyclic compounds, okay? And so, moving on to the cyclic substances. So again, if we had a cyclic substance, the chemical formula is CnH2n. And so what that means is if we had C6, we would have not 14 hydrogens like our acyclic counterpart, but we would have 12 hydrogens. And so we can see that if, let's just make a cyclohexane, okay? So cyclohexane has 6 carbons, and it is a hexagon, right? And so if we just kind of explicitly draw the hydrogens, we can see that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's 12 hydrogens. So that's kind of just proof of the concept. And while we're at it, why don't we just go back to the acyclic substance and kind of count out our C6H14. So let's make our straight chain example 6 carbons instead of 4. So 1, 2, 3, 4, 5, 6. And now I'm going to abbreviate all of these hydrogens because it kills me to draw out all the hydrogens. So I'm going to do just as blue, just so it's easier to differentiate. But we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, and so each of these ends of the blue lines is going to represent a hydrogen. And so that just goes to show you that there we go. We have 14. And so if you wanted to think about like how are these actually formed, or like kind of, I guess, justify the loss of those 2 hydrogens to give you 12 in the cyclic form. Well, if you kind of draw it like this, 1, 2, 3, 4, 5, 6, where our 3 hydrogens at the end are 1, 2, 3, 1, 2, 3. So this would be just hexane. It's got 6 carbons, okay, and it's an acyclic hexane. It's just a straight chain hydrocarbon. So if we had that, drawing this structure like this, very suggestive, almost in the ring, will help us identify basically or justify the loss of those 2 hydrogens to make that ring. If we wanted to combine this carbon right here with this carbon, make a bond between those in order to create that cyclic structure, we can do it like that, right? But now that carbon has 5 bonds, and so each of these does. This guy does, and that guy does, right? So what we need to do, whoops, I accidentally deleted that bond. What we need to do is actually remove a bond from that carbon in the form of a hydrogen, and then remove a bond from that hydrogen in the form of a hydrogen. Whoa. Sorry, I don't know if I misspoke there. Remove a hydrogen from each of those carbons, so that way that we only have 4 bonds for each of those carbons. And now the carbons are happy, and it kind of helps explain our CnH2n chemical formula. Okay, and so the only thing we really have to add to this column for cyclic structures is that the prefix for these, when we are naming them, is cyclo. Okay, so I did just call 1, 2, 3, 4, 5, 6. This was hexane. Okay, and this right here is cyclohexane. Okay, and so that's what we mean when we say the prefix. The prefix is coming in front of the word as opposed to a suffix that comes at the end. The prefix is cyclo for when you're naming these cyclic structures. Okay, so let's go over the number of carbons and their prefixes. Okay, and that's just basically for these straight chain hydrocarbons. Okay, so the number of carbons will be in this column, and then we'll have the prefixes in this column. I'm actually going to move this over a little bit because, oh, I guess that'll work. We have 1, 2, 3, 4, 5, 6. There you go, making weird shapes in my drawings. iPad. 6, 7, 8, 9, and 10 is as high as we're going to go. You can definitely go higher. Things get a little bit more complicated after that, but let me bring this over a little bit more. Okay, so the prefixes. If something has 1 carbon, the prefix for that alkane is meth. Okay, so like methane has only 1 carbon. And then for 2, it's eth, like ethane. Has 2 carbons, and then something that has 3 is prop. Not prop, but prop, like propane. For bute, like butane, and then it goes pent, and then it goes hex, and then hept, and oct, non, and then dec. Okay, and so there's a couple things we want to add to this. So as a parent chain, we want the end of a particular substance to be ane. So here, the end with ane. And so what I mean by that is 1, 2, 3, 4, 5, 6 carbons, right? Something with 6 carbons has the prefix hex, and if it's something that's called a parent chain, which we'll explain in detail in a little bit. It's basically the longest chain in that compound. Then we basically just tack on the ane as the suffix or the ending, okay? And so that means we have hex because it's got 6 carbons, and ane because it's basically just an acyclic hydrocarbon, okay? It's an alkane, okay? If it is a substituent, meaning coming off of that straight chain alkane, like a branched hydrocarbon, then we have a different scenario. So as a substituent, you end with YL, okay? And so what I mean by that is, let's say we had 1, 2, 3, 4, 5, 6, and then we've got this thing coming off right here. So this right here, we do have a hexane in there, right? So this portion right here is 6 carbons, so that would be a hexane, but this isn't part of the main group of that straight chain. So what we call that, we're going to isolate that as a substituent. It's coming off of the main group of the hydrocarbon. And again, this will be more clear later when we go over in detail the naming of compounds. But for now, just let's call this a substituent. And when you have a substituent, you can classify them using the prefixes with a different ending, which is YL. So since this circled carbon is only this circled substituent is only 1 carbon, we use the meth prefix, such as this, and then we finish it off with il, so methyl, like methyl or ethyl or propyl, butyl, pentyl, hexyl, heptyl. It depends on how large that substituent is. But so in this case, this would actually be called a methyl hexane because it's got 1, 2, 3, 4, 5, 6 straight chain carbon hydrocarbon with a methyl substituent, and there you have it. Okay. Now, in addition to that, let's just draw another example of, let's say, a straight chain alkane. Okay, so we got 1, 2, 3, 4. Okay, so if it's 4 carbons, okay, we want to call that bute, and since it's an alkane, we want to finish that off with ane, and so this is actually the structure of butane. So what if I drew this? So this is 1, 2, 3, 4. It's kind of weird. It's actually, so this is straight chain, and this is branched. Okay, so this being branched, it has 4 carbons in there, and so one of the names for this is actually isobutane, and it has the same chemical structure. It has the same chemical formula as butane, which is 4 carbons, and 4 times 2 is 8, plus 2 is 10 hydrogens. And so you don't even need to count the hydrogens anymore. You know that this particular formula right here is going to tell us what the number of carbons and hydrogens are for straight chain, and then for this one right here for us if it has a ring in the structure. Okay, and so the point that I'm trying to make here is that this particular structure right here can be called isobutane, and it does have the same chemical formula of C4H10 and C4H10, but they are not the same chemical structure. They are constitutional isomers. Constitutional isomers. Whoa, 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 whoa. Constitutional isomers. Okay, and so basically what this means is that they have same chemical formula, but different bond connectivity. Okay, so but different bond connectivity. Okay, and that again is a constitutional isomer. Okay, so this is really important that we're aware of this. Some other examples could be 1, 2, 3, 4, 5. This is pentane. We can have 1, 2, 3, 4, 5 carbons, and then 1, 2, 3, 4, 5 carbons. And so, as you can see, with this just 5 carbons and 12 hydrogens, you can have quite a variety of structures, right? And the more carbons that you get, the more constitutional isomers that you can create. And so it gets really complicated, but that's not necessarily something you'll need to do. But a very common question is, what's the relationship between these structures? And so basically you would be given these three, and then what's the relationship? Well, they have the same chemical formula, but there's different bond connectivity, and so they are constitutional isomers. Constitutional. Here, how about this? There we go. They're constitutional isomers, okay? So another point to make on that is sometimes it gets really complicated when you have larger structures, and you have to remember that bond rotation is okay. And so, for example, this one right here, it doesn't have to always be drawn like that. So this one could be drawn upside down, okay? Or it could be drawn like this, okay? Or it could be drawn like this, or another way. And so these might all look like they are different structures and that maybe they're going to be constitutional isomers. However, this is just rotating about those chemical bonds, those sigma bonds, and just kind of giving you a different, not three-dimensional structure, I guess, because it's on paper, so a different two-dimensional structure. But they are, in fact, all the same compounds. And so these aren't constitutional isomers. And so it's really important that we are able to differentiate between those. Okay. Now, let's go back to our cycloalkanes. Cycloalkanes. Okay. So remember our cycloalkane formula was CnH2n, and we gave our example of cyclohexane, which was a C6H12. Okay. Now, some other examples. I guess the simplest cycloalkane is here. It's a triangle, right? You can't have a circle or a cyclic structure with less than 3 members. And so we've also got this guy. We've got a pentagon, right? And then we've also got our hexagon, okay? So these are some very common organic chemistry structures that we're going to see, and we want to remember we got that chemical formula, right? One thing, let's go ahead and just think about the naming of these, and so we'll go into what it's called nomenclature in a separate video, but since this has 1, 2, 3 carbons, let's go back up here. We've got 1, 2, 3 is a prop, okay? And so since it's an alkane, we would call this propane, right? But it is a cyclic structure, and remember the prefix for cyclic structures had to be cyclo, okay? And so this is just cyclopropane, okay? This one right here is 1, 2, 3, 4. This one right here is cyclobutane. And then this one right here is cyclopentane. And this one right here is cyclohexane. And that's pretty much it for the basic cycloalkanes. Remember, we've got our straight chain, and then we've got our branched, where we can have branches all over the place. It can get really complicated. And then we also have our cycloalkanes, which are forming rings, with 3 members being the smallest type of cycloalkane that's possible. Okay? All right.